Good, there we go. Okay, positive. Okay, good. So now with that, we are now able to add and subtract rational expressions, right? Again, theoretically, what we have to do is we have to be able to get a common denominator, okay? That's really what matters. Okay, but once we know what that LCD is, that common denominator, you have to manipulate each rational expression, right? You have to manipulate it, just like you would with a fraction. Basically, you multiply the top and bottom by whatever's missing, so to say. So if the LCD was b times c, here you just have b, right? Okay, so you multiply the bottom, the denominator by c. But remember, whatever you do to the bottom, you do to the top. So you have to multiply the top by c as well. So that's what we do. And that's what we're doing here, right? You're basically rewriting each rational expression in an equivalent way. So the denominator is the LCD. Yeah, you may have to use this rule more than once, but that's okay. That happens. Okay. So let's do some examples. So let's suppose we want to add these two rational expressions together. Okay, so notice that the denominators, they're factored already, right? You can't factor these denominators any further. Not only that, they each have exponent 1, right? You know, you have 3x plus 2 and x minus 1. Those are irreducible factors themselves, and their only exponent is 1. Okay, right? You can't factor out 3 from 3x plus 2 because 3 is not a factor of 2. I know it's tempting to do that, but you really can't do that here because here we're working over polynomials whose coefficients and constant terms are integers. That's really what we're doing here, even though the roots can be rational numbers. That is solutions to the polynomials equal to 0. Okay, so from here, we get the LCD is just a product in this case, which is nice. You know, it makes it a little bit easier. I mean, their only exponents are 1, but again, we don't have to write them. So what do? We have to rewrite each rational expression. So its new denominator is the LCD. So we have 1 over 3x plus 2 here, right? What do? Well, we're missing x minus 1, right, in that denominator. So we're going to multiply the denominator by that. But remember, whatever you do to the bottom, you do to the top. That's what I'm saying here. You know, I'm just using this rule, so to say. And from here, we get x minus 1. Well, 1 times it, which is x minus 1 itself. And the denominator is 3x plus 2 times x minus 1, as you can see. Okay, that's for the first rational expression. For the second one here, right, we have x minus 1. We're missing 3x plus 2. Okay, so we multiply the denominator by it. But again, we have to multiply the top by it as well, the numerator. And that's why we have this. And so from here, we get this. I mean, I know the 3x plus 2 I put on the left side, but that's okay. Mostly because I wanted the denominators to look the same. So this is what we get. And now to add, right? We actually add them like so. Okay? And now we're adding. So that's what we're doing. Again, we leave the numerator, the denominator, excuse me, we leave alone. We combine the numerator. Now here we want to simplify. So here we actually do have to multiply. That is, we do have to multiply, actually. I mean, it's not hard to do. It's just basically you're just going to FOIL. Okay? So we have, when you multiply, you get 9x plus 6 minus 3x squared minus 2x, like so. Okay. And so after you do all that, you combine like terms, this is what we end up with down here, which algebraically is this. This is what it is algebraically. So we want to see if this is simplified. I mean, what's nice about it is the denominator is already factored. You could try factoring the numerator. I mean, I would probably try the AC method. Okay? I mean, here what I did was I just wrote down that the denominator will be 0 only when x minus 1 is 0 or 3x plus 2 is 0. And there, of course, you get that x has to be either 1 or x has to be negative 2/3. I know in the first example today I didn't show this. I definitely should have, so I apologize for that. Here I'm just showing that this is only going to be 0, right, when x is 1 or negative 2/3, because I'm going to use the factor theorem. So in other words, we could factor the numerator. What I'm going to use instead is the factor theorem. So let's say capital F of x is this. Okay, I'm not sure why I have a question mark here, but let's say this is capital F of x, okay? If we plug in negative 2/3, right, for x, we don't get 0. And if we plug in 1, we also don't get 0. So that tells us that this is simplified. In other words, here, let me go back to the previous slide. I know I'm going back and forth. In other words, since the numerator does not have 1 or negative 2/3 as roots, that tells us that x minus 1 is not a factor of the numerator, and 3x plus 2 is not a factor of the numerator either. Okay, that's really what I'm saying here. To be simplified by the factor theorem, this equation cannot have this as a solution or this as a solution. And from the next slide, as I just showed, it doesn't. So it is simplified. All right. Are there any questions about that example? Oh, this is driving me nuts. Question mark. I don't know why that's there. Any questions about this one? I mean, you probably could have used the quadratic formula to see what the roots of this are, or you could have factored it if you wanted to. Okay? What I'm showing here is that really, in a sense, we can get around both of those. So, yeah, someone had a question?
How did you get negative 3x squared plus 8x plus 5?
Oh, from here, do you see, like, do you understand this part here?
Yeah, so you're multiplying the denominator by the top and the bottom to get the same denominator, right?
Right, that's what we did. That was on the previous slides, yeah. That's what we did here. And then when we added, we had the denominators are the same, right? So we have to combine the numerators. Looking at the numerators here, right, there's not much we can do at first unless we multiply this, carry out this multiplication, and that's what I did.
Oh, okay.
Does that make sense, or?
So, I got, yeah, now I see what you did. Okay.
Okay.
Thank you.
Oh, you're welcome. Good question. It's good. Okay. Are there any, good question. Are there any other questions? But again, you could have used the quadratic formula here. You could have. I thought that would be not too complicated, but might be too tedious, although it's not terrible. Or you could try factoring this. So either way. All right, let's do one with subtracting. It's the same idea essentially, right? In that we need a common denominator, right? We need a common denominator. So here, notice the first rational expression, the denominator is not factored, right? Right? It's x squared minus 25. 25, though, is a perfect square. It's 5 squared. So we have a difference of 2 squares here. And that's how we got this factorization. You know, this is basically x squared minus 5 squared. And that's equal to x minus 5 times x plus 5. Now, that's for the first rational expression. For the second one, the denominator is factored. You can't factor this down any further. So to get the LCD, the irreducible factors, what are they? Well, from here we have x minus 5. Here we have x plus 5. Here x minus 5 is accounted for already. And what about the exponents? Well, the only exponent of x minus 5 is 1. Here it's also 1. X plus 5, the only exponent is 1. So what's the LCD? The LCD then is just x minus 5 times x plus 5.